Are you going to write on the left side of the board?
Where you tell me where not to write, and I won't write. Can I write here?
Right now, I can't see you at all.
Okay.
But there is a possibility to like make the camera move where you go.
Yeah, so I thought it was less, it wasn't as good. Should we have the camera move? Is it better if it moves or if it better if it zooms out? So can you see this?
Yes, this I can see fine. I think it's better if it moves.
So. I don't know.
Oh, yeah. Yeah, that's great.
Better? Okay, let's try it. But it doesn't zoom in that much, so I don't know. Okay, so anyway, but you don't need to see everything you can do in your head. Yeah, I forgot what it is. Okay, just for the people who are taking the course for credit, there will be exercises or exercise sheets that I will give out, hopefully, once every 2 weeks, and a final take-home extended exercise sheet. This is what I committed to with the administration, but I will need to, but I won't be giving a grade. So it's just pass fail, and if you hand in the exercises, even if you solve them wrong, then you still get credit. So all you have to do is hand in the exercises, which means send them to me by email. You can give me a hard copy, but it will be. I'll try to take a look at them. Hopefully, I will have time. But and if you want me to do some of them in class, it's also a good thing. If in general, I will also probably give lots of exercises doing things for you to think about for yourselves. And if you feel that you get stuck, you should ask me to do it in class, because sometimes I might think that details are obvious to or maybe not obvious, but easy enough to do on your own, and I'll give it to you because it's good to think about these things. But if you find yourself getting stuck, then it's good to let me know so that I know where you are. Logistically concerning, today and tomorrow we'll be here in this room because the university has exams, so we can't do the other. Usually Wednesdays there is some building 72 in the hidden corridor. I don't know if everybody, Alaka, you should go with someone. There's a hidden corridor. It's like in Harry Potter. You have to find it. That's usually, but tomorrow we'll be still be here as an exception, and next week as an exception we will not meet at all in person because I'm going to be in Austria. So what we'll do Zoom sessions at the same time. Hopefully, I think Wednesday I have a talk it exactly when the course ends. So I have to see that they don't need me to be there a bit before, but we should do it basically the same times here. Yeah, and then the week after it's Yom Ha'atzmaut, so probably something.
That's the end of the semester.
Follow the announcement. Yeah, okay. Yeah, semester is short. I don't know how much I'll be able to do. Hopefully, I'll be able to do most of an elementary proof. So everything here, what I'm going to try to do, should be accessible to anyone who has basic undergraduate studies, and even simpler to anybody who knows probability, measure theory, really the basics, and I'll go over what you should know, and the definition of what a group is, and and what a normal subgroup is. You should know this. That's basically what you need from group theory. Quotient groups, things like that. Okay, you know, like the very, very basics, and so say I would say the first half of the 3 courses given here at BGU of probability, measure theory, and group theory or algebraic structures or whatever it's called. And you just need to know the first few weeks of these courses. You don't need to know CELO subgroups or I don't know what. And if you know what a Hilbert space is, it's maybe an advantage. But I'll say something about that. It's basically linear algebra, but not much more than that. Okay, so I'm trying to be very elementary. So this is an elementary proof of the following theorem. So theorem, 1981. This is basically, most of you owe your careers to this theorem because this is basically kickstarted what's called geometric group theory. Not exactly, because already before that, there were people like, well, let's say Milner was doing geometric group theory, and he's really the founding father, I would say, of geometric group theory. And luckily, there are no big shots in geometric group theory sitting in the room who can contradict me. But Milner asked a lot of questions, like in the 1968 American Math Monthly, there was a list of questions posed by Milner. One of the questions was, do there exist groups which do not have polynomial growth or exponential growth? So do there exist groups of intermediate growth? I will go into all these notions. I will exactly define them. If you don't know what they are, it's okay. But I'm just saying that for the moment that was a question that appeared in 1968 in the American Math Monthly. In the same year, Milner and also Wolf independently proved that nilpotent groups have polynomial growth. Okay, that's when so these were the first theorems that were proving things geometrically about groups using the algebraic structure. You start with nilpotent, that's an algebraic thing, and you end up with a geometric thing, growth. Okay, so you end up with something about a metric space. And then another question that Milner posed in that same question, there was this like a list of questions that 1968. Another question was, can you characterize nilpotent groups? After knowing that nilpotent groups have polynomial growth, Milner asked, can you characterize nilpotent groups using some geometric condition? And then Gromov eventually did that a few years later, quite a few years later. So in 1981, it appeared, I guess he knew already the proof beforehand. And so this is theorem 1981, Gromov. It's known as Gromov's theorem, but many theorems are known as Gromov's theorem. So we already know that nilpotent groups have polynomial growth. Any finite extension of a group should have the same growth as the group itself. We will prove that when we define what growth is. So virtually nilpotent groups also have polynomial growth. Gromov said, oh, well, these are the only examples. Okay, so only these groups have polynomial growth. So the theorem is
virtually, what do you mean by that?
I'll define it. Virtually nilpotent if and only if polynomial growth. Now, I'm not being precise here because we didn't define anything yet. We didn't give any definitions. So virtually means you have if virtually P for group property P means that you have a finite index subgroup with property P. That's what it means. Okay, it's the same as saying P by finite. You know the by notation. But I'll talk about it in the future about this virtually thing. You have to do virtually. Whenever you're doing geometry and groups, you have to do virtually because finite index usually does not change geometric properties. Okay, because it's basically the same geometric structure. So, I mean, what you can think about is you have, suppose I have a copy of Z, right? I have this geometry and take a finite index. So I take two copies of Z and connect them somehow, right? The same geometry, right? It's not really large-scale geometric properties are not affected by this. So that basically captures this idea that geometry shouldn't care about finite index. Okay, so so this was a very, very deep theorem and complicated theorem at the time. I could not teach you a proof of this using Gromov's original paper. So it uses the solution to Hilbert's fifth problem. So it uses very deep mathematics, Lie groups, and so what basically Gromov does, okay, so what was the difficult direction? The difficult direction was starting from polynomial growth and saying that I have a virtually nilpotent group. The other direction was already known by Milner and Wolf. Proof is a bit technical, but not very difficult. Okay, because nilpotent groups, we'll talk about them, we'll see, you have a structure where you can grow them easily by taking Z extensions. Okay, and all you have to understand is if you have an nilpotent group and you do a Z extension of it, what happens? And so basically they could analyze it that way. that's not exactly how the proof that these grow polynomially goes, but there was another theorem same year in the end of the 60s where Milner and Wolf proved that if you have a solvable group, then it's either of exponential growth or polynomial growth, which is what prompted Milner to ask the same question. Do there exist groups which are not solvable, which have this intermediate growth? Solvable groups don't have intermediate growth. And kind of the ideas running around all those theorems were the same ideas, but Gromov brought a completely new thing to the table, and Gromov starts with a polynomial growth group. So this is the difficult direction. This is, this is hard, we'll say. Well, harder than the other one. And you start with a group, all you know about it is that you have symmetric on it with some K-graph which has polynomial growth. And then you have to go from that and you have to deduce some algebraic structure. Say something about commutators. Right? Where do they show up, right? So what Gromov does is he rescales this metric space. He looks at it as a metric space, rescales it, takes a limit. The limiting space is going to inherit some group structure. It's going to live inside some Lie group. In that Lie group, you have Hilbert's fifth problem. So you can classify Lie groups, and then you can work some magic. So it's a lot of really, really deep mathematics. I would, I could never teach you this. I don't know it myself. It's just a very, very complicated proof. Very non-elementary proof. So then the years went by and there were a few new proofs appeared. So for this theorem. So this is what I want to do. I want to teach you an elementary proof for this theorem. Okay, that's what I want to do. And what I'm going to use is I'm going to use probability. So of course, okay, so we're going to only prove the harder direction. I don't know if I have enough time. And also the other direction is just technically working with commutators and doing things properly. So we're going to prove this direction. And our main tool is going to be probability. Okay, so the main tool, we'll give the elementary proof, is going to be harmonic maps. And the word maps here just means that they take values inside the Hilbert space instead of taking values inside the R. Okay? But it's, if you know what a harmonic function is, the same thing. And harmonic maps and martingales, which is basically the same area, will convince you, hopefully this week, that martingales and harmonic functions have to do something with another, and random walks. Okay. And looking at these, this is kind of new. This is kind of new. I just want to give you kind of the overview, which is where these come up. So again, questions for this started at the end of the 60s, beginning of the 70s. Okay, Gromov proved this in 81, or maybe at the end of the 70s, and published it in 81. And these tools, so random walks on groups. First of all, random walks have been considered since the 20s by Polya. Polya only looked at ZD. Okay, so only on the Euclidean lattice, sums of independent random variables. That's basically what a random walk is. Okay, but starting to look at random walks on general groups, and we'll go through all of these things. We'll define everything here. This, I would say, the founding father of this is Kesten. So, Kesten's thesis in 1958 or 9. Okay, so there Kesten tied random walks on groups. He gave a condition for amenability. Amenability is another algebraic property of a group. I would say functional analysis property, but anyway, it's a property of the group. The group can be amenable or not, and Kesten gave a criteria for this in terms of random walks on that group. Okay. I don't know how much time we'll have, if we will go into it or not, but so Kesten started looking at these objects, and then they were later looked at by Kesten, and Furstenberg also started with matrix groups, which have more structure, and then This was developed further, and martingales are a classical object. These have been looked at since the birth of probability. So since the 20s, people have been looking at these definitely, and harmonic functions well, they're classical objects. These goes back all the way to the 19th century, right? But to look at them in an abstract way, this is a bit more modern. And the connection here, I would say, between the ability to use harmonic functions, random walks, and to say things about a group, I would say that maybe the really first connection was by Kleiner. So this is 2007 or 9, depending on if you look at when it was on the archive or when it was published. This is new enough for me to remember. I was already remember when this paper came out. What Kleiner did was he said something about the space of Lipschitz harmonic functions on a group. Okay, he said, well, he proved that this is a vector space, and it's easily seen to be a vector space, and he proved that the space has finite dimension if you have polynomial growth. Now, where did Kleiner get this idea? He got the idea from Yao. Okay, so Yao was looking at harmonic functions on Riemannian manifolds. Now that already is classically, right? Going from harmonic functions on Euclidean space to harmonic functions on Riemannian manifolds is not difficult because Riemannian manifold looks locally like Rn, right? So saying what a harmonic function is very easy because harmonic function is also a local condition to be harmonic. And classically, I mean, classical, mathematics from the 19th century, your harmonic function, if you have the mean value property, right, at every point. So looking at manifolds Riemann already understood that you can look at manifolds and harmonic functions. And, and they have all this analytic continuation and stuff, and these are very important. So Cauchy and all these people were looking at these things. This is very, very classical, but Yao, this is probably around the 70s, was looking at these things. Okay, and he had a conjecture that so Yao, for example, proved that Riemannian manifolds with non-negative curvature do not admit non-constant positive harmonic functions. Okay, so you cannot have a non-trivial positive harmonic function if you have like a sphere or something like that. Or Euclidean plane or Euclidean space is also non-negative curvature, right? So yeah, and that we already know that's called Liouville's theorem, but actually Cauchy was the one who proved it. So so that was kind of classical, and then Yao did it for manifolds, and then Yao conjectured that I think this was 78 or something like that, if you have a manifold with non-negative curvature, then the space of Lipschitz harmonic functions on it, so functions that are both harmonic and Lipschitz, I will define all these notions. That space should be finite dimension. And this conjecture was solved by Kolding and Minicozzi. I cannot write Minicozzi, I don't think that. Probably made a mistake somewhere. Anyway, so they solved it 90 something. Okay, I don't remember the year. And Kleiner basically took their proof and adapted it to the discrete setting, okay, to Cayley graphs. Now, what was the difficulty, the big difficulty, and Kleiner did, it's a very, very subtle proof, very, very subtle. I tried for a long time to generalize it, and like every step there is important, and you have to really use polynomial growth. You cannot go beyond polynomial growth. So the difficulty in going from Kolding and Minicozzi to this case is that on manifolds are very, very different as geometric objects than discrete metric spaces, than Cayley graphs. Because manifolds, you have zero distance. You can go as close as you want to a point. And on graphs, you cannot go. There's a fixed minimal distance that you can go to a point. And this gives you a lot of problems. In general, analysis breaks down, or if you want to do discrete type analysis, which we will do in this course, you have to be very, very careful because you cannot send the errors to zero. You cannot kind of get rid. Things are very nice in the continuous space, become much more difficult in discrete space. Okay, yeah, one of the things that you get from that is that if you have a manifold of non-negative curvature, it's basically almost automatic that you have nice geometric properties. For example, you have what's called the doubling property. I won't say what that is, but you have some nice property that you get. And this is just not true if you have a K graph. Okay? You don't have the doubling property given polynomial mode. Well, you do have the doubling property, but you only get it a posteriori after you know Gromov's theorem. Okay, so you cannot get it directly from the polynomial. Okay, so in manifolds you have a stronger property that kind of comes automatically from the definition of non-negative curvature, and I won't even talk about curvature in this course. It's a very, very active subject today, curvature, and proving things under curvature, or what is even the right definition of curvature on a graph. One of the problems we have, again, in discrete spaces, the analysis becomes difficult. Things that say the same thing in the continuous space don't say the same thing. You start becoming different definitions, compete for your attention. Okay, so this is a very wide overview of what I want to do, what I plan to do on this course. Okay, and let me mention one more proof that I'll use. Ozawa in 2018. Beautiful paper, 2 pages, proves Gromov's theorem, but you basically have to know functional analysis and be, up to date on. I mean, Uri gave a course on Ozawa. He gave a talk on Ozawa's paper. He gave 2 hours, went through the whole paper, but basically you cannot understand anything if you don't know you have to speak Uri's language. So you need background to understand what he's talking about. Space of cocycles, whatever. So I want to do all that stuff. But basically, the proof I'm going to give you is an elementarized version of Ozawa's theorem. Okay, an elementarized version of, so digging into what the definitions are, and also some twists in proving things maybe probabilistically and not using functional analysis. But basically, this is the game, and I will try to present things that are open or unknown during our discussions. And also, there's a big motivation to understanding more and more proofs of Gromov's theorem. You could say, okay, why do we need to understand proofs of Gromov's theorem? Why is it useful? Well, it's not useful for the application itself, but we have a big conjecture. This is one of my favorite open problems, and of course, this is not a good question for a PhD, okay? Because you will most likely not solve it. If you do, come tell me, we'll write a paper together, okay? No, okay, so conjecture is that, and I didn't define the notions in the conjecture, but it's tied to this, so I'll say that this is called Grigol-Chuk's, and I'll come back to this gap conjecture, or the gap conjecture. And let me phrase it. Grigol-Chuk is very optimistic in his conjecture, so you can phrase a family of conjectures. Okay, so there do not exist. Now you can see why it's hard, right? Because proving something doesn't exist is usually hard. Right? They do not exist. Finitely generated groups of super polynomial, which, knowing Gromov's theorem, super polynomial just means not virtually nilpotent, right? Same thing, not virtually nilpotent of super polynomial, but growth smaller then I leave this open. That's why I called it a family of conjectures. You can plug into a function. So Gregor-Chuk will plug in a function like this, or Chuk conjectures. But also in one of his papers, he also already formalizes it as a family of conjectures. He has a parameter beta, and he says there doesn't exist then growth, which is most exponential of radius to the beta, and here beta has to be some number which is less than a half. Okay, now I don't know what the reason is for this strong conjecture. The only thing is that Gregor-Chuk was the first one to find groups of intermediate growth, and his group at the time had a certain property. So that was also in the beginning of the 80s, 84 or something like that. And Gregor-Chuk's group or family of groups, these were the first examples of intermediate growth, answering again this question by Milner from the 60s. And his group has a certain property which guarantees that the growth has to be larger. It cannot grow slower than exponential to the square root of r. And in fact, it was only recently, quite recently, a few years ago, determined that the actual growth rate was pinned down by Tianyi Zheng and Anna Erschler, and they computed the exact exponent, which is bigger, strictly bigger than a half. It's actually strictly bigger than a half in the Gregor-Chuk group. Okay, so there are no groups even with beta equals to a half. There are no known examples, but because the property that many of the examples we have today, and including Gregor-Chuk's group, has like a certain property which easily tells you that the group growth cannot be too small. And Gregor-Chuk, I think that's why he conjectured beta less than a half here. But I would anything. It would be fantastic if you can put in anything here. If you can prove any function here which is super polynomial. Okay, polynomial is, we know that there are groups, so you cannot say that they're not so super polynomial, but growth less than, say, maybe some log here. Some, let's call this maybe alpha. Alpha bigger than 1. You do any alpha bigger than 1? Fixed alpha bigger than 1. Alpha equals 1, it's polynomial, right? Exponential of logarithm. You could put a constant here, so it's just polynomial. So can you do any alpha bigger than 1? State of the art. There is something known. There is something known. This is something in chapter 9 of Tao, Shalom and Tao. Shalom. Oh. That they have a 100-page paper where they basically take Kleiner's proof and put it, into its fundamental particles and then put it back together, and they get it quantitatively, and then they can say a lot of quantitative things. And as one of the corollaries of their work, they get here a bound, so they get the gap conjecture for a function that looks like this. So you always have log r, right? Because this is polynomial, and you want something super polynomial. So the correction here is going to be log r, some epsilon. Epsilon can be figured out. It's some very small number, maybe 1/100 or something. So this is the state of the art node. So there are no groups smaller than this which are not virtually nilpotent. But proving that is very, very difficult. It's really a long and technical paper. Goes through the motions in Kleiner's paper, but really like everything, instead of defining a harmonic function, you define an almost harmonic function, or you have like 3 parameters and epsilon r k harmonic function, and then you have to do always follow all the parameters, and you get like 17 parameters at the end, and you have to figure out everything, and it's very, very hard to follow what's going on. Okay, maybe at the end of the course, I will talk about some strategies on how to attack this. Of course, I don't really know how to do it. Otherwise, I would be working on that. But this is a very difficult question, been open for years. Gregor-Chuk presented this question in the 1990 ICM. And there's big motivation for these proofs, because if you can generalize, if you can replace polynomial growth here, in the hard direction, if you can replace polynomial by something super polynomial, then you've proven a gap. Okay. Prove some growth implies virtually nilpotent, that implies polynomial, right? So you've proven that you cannot have small enough growth. It's not polynomial. Okay. So yeah. And there are some results. Alex Lubotsky has some results on this with other people. There are some results for families of groups. Again, Milner-Wolf already in the 60s knew that for solvable groups, you have either exponential or polynomial, even a bigger gap than what you get in real, in general. But for general groups, there's no, so some family pro-finite P groups, I don't know what, maybe Amit knows. I have no idea about all of these families, but some families, they have these things, but you can say things, but not a general criteria. It kind of just takes in the geometric information and gives you nice algebraic information. No, not a lot of theorems that can do that. Okay. Any questions?
Do you normally follow a book in this course?
Yes. So there's my book. It's on my webpage. It's also, there is a course website. So I sent out an email, right? There's a link there for the course website. I never remember the name. It's a Google site, so it has like a long link. The course website will have, I'll try to keep it up to date with announcements, exercise sheets, solutions. There's a link there to my book. You can also just look for my homepage, and there's a link on my homepage to the book. What else did I want to say about that? Yeah, so I basically found it, but I'm not doing it like in order. It's too long to go through the whole thing. So, but if you ask me, I can tell you today I'm doing things from chapter 2. I think I'm doing things from chapter 2, but you can easily find them by topics. I mean, you just look at the beginning of the book. There's a table of contents and also a list of notation and so if we do a martingale or stopping time or something like that, then you'll find it in the list of notation. You click on it and it goes to the place where I define it. So that will be the area where I'm talking about.
That's your book on random walks, right?
So it's a book. So the book is called what's it called? Harmonic functions and random walks and groups. Okay, this is the name of the book. Okay, and if you have influence on a library, then ask them to buy it. I don't expect that. One of my conditions was that I'm allowed to keep a free copy on my webpage. Don't expect anybody to buy the book, especially since they made it more expensive than I wanted it to be. But if you have a library, it comes out of Israel Science Ministry funds or EU funds, or if you have influence in Budapest or in Prague or something, and have them buy. Next week I'm going on a book tour, so I'm going to.
Are you gonna sign?
Apparently, if they buy the book, I get like $1 or something.
Don't we all have influence at Ben Gurion?
Oh, Ben Gurion, I've already asked them to order the book. Yeah, they pre-ordered it already.
Just one
It should
shot?
be out. It should be out. I think it should be out during May. So really, it's right now. These are pictures. The book has pictures. So it's a special book, very special.
I had many books bought by many libraries.
Yeah, so if you write them like, this is a great book, buy it.
Okay.
Well, I mean, I think it's a nice book, but don't kill yourself convincing people to buy it, and definitely not somebody from their private libraries spend so much money on crap, they can buy this crap also. Okay, so yeah, Ben Gurion is buying it, and I also asked friends in other Israeli universities. No, but that was just selfish and you can download it from my webpage. It's free. I didn't do it to become rich. Okay,
Ariel,
yes.
so, Phenomenal did prove that there exists a gap,
Yes, this is the gap.
so this is
There
some
is a
gap.
gap. We know there is a gap.
Yeah.
There is no reason it should be this function. There is no real
So the question
reason.
is what
It's
is-
just the limitations of their methods. It's just the limitations of their method. In fact, it really seems that working hard, technically one can improve. The best person to do that today would be Matt Toynton because they know a lot more about approximate groups and things. So everything there, you have to kind of take all the notions that I will say in this course, the group theory notions and the probability notions, and you have to turn them into, you know, an A, B, C, D harmonic function, G, H, F, K approximate group. You know, you have to make everything quantitative and then follow like. Basically, the only guy who can do things like that is Terry Tao, and but Matt Toynton has already quite a few papers on these things, and he understands them well, and they've used them to classify finite transitive groups or finite transitive graphs of polynomial growth, and you know, finite graphs again more difficult because you have to stop at some point. So you have to say, you know, what do I see? What is large scale? What is small scale? These papers tend to be very long and technical, and they don't have like a nice. I'm hoping that is not a direction I will try to go to, but I think if they do, they might be able to improve these things because they know some more delicate versions of Gromov's theorem. Like they can control. What does it say? If you have polynomial growth, so this comes with a number in it, which is what is the exponent in the polynomial? What is the degree of the polynomial? Take that number, you translate that number into, you can find a virtually nilpotent group, right? So there's an index here. So you translate that number into the index. And in fact, it's not exactly because you have to divide by a finite group, which the theorem is true, but you can get more exact information by saying I have a finite index with a quotient with a finite kernel, which is nilpotent. So the two finite pieces you can quantify using the exponent of the polynomial growth, and it's tight because there are examples where this is what happens, and they can get this, you know, this better version of Gromov's theorem. A few people go into that, and I don't remember the names, and I think they have the best chance of improving by just, you know, a brute force doing everything, you know, exactly properly in the right way. Okay, but kind of to break this gap, to break this barrier, kind of stretched exponential or even polylog, I don't see how it will come out of those things. And you need kind of a new idea. Yuda and Terry Tao, what they did was what they wanted really to do was to show, can a computer check if a group is of polynomial group, an infinite group? Right, okay, so their paper, there's a way of checking. Tell the computer, so finite time, right? So the computer has to go through, you know, look, so it can only look at a finite ball ever, right? So they have a theorem which says there exists, for every D, there exists an R0 such that if you find that scale R0, you know, that the group grows at most of polynomial with degree D, and you only need to look at a ball of finite radius, see if your group has polynomial degree D growth. Okay? So you can decide, you know, if your group is a polynomial of degree at most 5, and decide in finite time. Degree at most 7, it's in finite time. So it's not exactly what I said before, but it's for every degree you can decide in a finite ball. And that's what they were going through. It's an effective, they call it effective version of Gromov's theorem. The theory of approximate groups also gives other things. That's completely different papers of Green, Tao, Uyad, other people who do approximate groups and has other motivations. It comes from, you like these things of sum products, right? So some products have to do with approximate groups. Approximate groups just means that they're almost groups. What does that mean? Well, whatever. And you understand that you have to follow some quantification. Okay, maybe then we do take a break and then I do, unless there are more questions, we didn't really teach anything, but. Okay, so, take a 10-minute break. So, now we start getting our hands dirty. We're doing really mathematics and not, you know. I don't know. This is what separates us from the other. From the other departments in humanities. You know that math is not science, it's humanities. Don't do experiments in math. Okay, so I want a quick refresher on conditional expectation, seeing as I promised you only need undergraduate probability, so maybe you didn't do it. And also, I think it's a good thing to know, general. Okay, so definition and theorem. You know, I have to say that something exists if I want to use it as definition. So this is a definition and theorem. Okay, so if I have a probability space, okay, so this means sample space, right? I have a sigma algebra on this sample space and I have a probability measure on the sigma algebra. If you don't know something that I'm saying, please tell me, even if I tell you, okay, I'll sit with you after the course and tell you where to read or teach it to you, but just stop me if I say something that any object that you don't know. So I have probability space, I have a sub-sigma algebra, so a collection of events which forms a sigma algebra, and it could be smaller than the actual sigma algebra that we have in the background. Okay, and we also have an integrable random variable. Integrable just means that it's in L1. Random variable is a measurable function from omega to r, and the absolute value of x has finite expectation. Okay, that's what integrable means. Okay, then we can define the conditional expectation of x with respect to the sigma algebra, sub-sigma algebra G. Okay, so we define conditional expectation of x conditioned on G. Okay, this is just notation for something. Okay, what is this? This is, so let me write down the name of this thing so that you know what I'm talking. So the conditional expectation is x conditioned on B, or conditional expectation x conditioned on G.
Yeah.
Mhm.
Is the same object as the conditional expectation in a general sister algebra?
I don't know what the conditional expectation of the C-star algebra is. My guess is that they have some connection, but I cannot say. This is the classical object called conditional expectation, which has been known since almost the beginning of the 20th century. So this is something classical. And I define this object. This is a random variable up to measure 0. So it's only defined up to measure 0, right? It's a function. It's going to be in L1. So it's going to be an L1 random variable. And again, L1 random variables are only defined up to changing measure 0, right? You can take very different versions of them up to measure 0. Okay, measure is this measure. So it is the random variable. And say if we were talking up to measure 0, such that this is defined to be the random variable such that for any event A in my sub-sigma algebra, okay, take for any event, if I take expectation of my newly defined random variable, right? This is just a random variable. Think of it just y, okay? Take this, I multiply this random variable by the indicator of a, I get a new random variable, okay? And I take the expectation of this whole thing. This expectation exists, well-defined, everything is good. I mean, this is going to be an L1 random variable, so it will be good. And it's the unique random variable which satisfies for any a. When I do this operation, I get the same thing as just using x here. See, the x and this kind of interchange. Okay, now why did I say definition slash theorem? I said definition slash theorem because you have to prove that such an object exists and that such an object is almost surely unique terms, so that if you
G measurable.
yes, thank you. Yes. For any such that right is the G measurable random variable. Of course, because otherwise not be unique. It's G measurable and it has that property. Okay. Let me explain a bit the intuition behind these things. So first of all, one way to think about sigma algebras is think about them as information. A lot of times when I teach probability, then I say, okay, what is the sigma algebra generated by some events, right? You take the small minimal sigma algebra that contains some event. Well, you take some events, you want to turn them into a sigma algebra, so you have to take unions and complements, and then you have to take unions of those things and also complements again, and you do this infinitely many times, you get a sigma algebra. Well, you can define this using transfinite induction, but it's easier just to define it in a different way, right? But you can think of sigma algebra generated by some events as the information content that is in those events. Right? I can ask, did A happen or A not happen? Did B happen or B not happen? But I can also ask, did A and B happen? Did A or B happen? Right? So you can generate a whole family of things from some events, and kind of the sigma algebra is the information that you have. Right? Measurability means that your functions kind of are standardized with respect to the information that you're talking about. And when you want to do it, when you take a sub-sigma algebra, then my random variable is not necessarily measurable with respect to the information G. What I want to say is I know everything in G. Right? I know everything happening in G. All the events there, I know if they happened or not happened, and all the combinations that I can think of. So I have all the information in G. Now I want to say, what is the average of X given that information? That's the intuition of this thing. And I'll write a formula down, which will be much more convenient in specific cases for what this looks like, and you'll see what happens. So basically, it's like this. You sample from your probability space, you look at the little omega that comes there, and then you say, well, what is this? Well, it's kind of the average value of X, but kind of, I know that this little omega had to come from events in G. Something like that. Okay, I'll make it more precise. But if you should think about it, if expectation in general is kind of where the center of mass of the random variable is, where I should balance it. If I weight realign by my random variable, then where should I put it so that it's balanced, right? This is the same thing, but you're kind of conditioned on the information on G. You know G. Okay, that's why it's a random variable. This is not a number. This is a random variable. Okay, well, it's not necessarily a number. Okay, it's a function of omega. Okay, now, usually it's very, very hard, and you should never use intuition to talk about conditional probabilities and conditional expectations. Intuition is misleading. Even if you do it for many years, intuition is very, it's not, it'll take you to the wrong place. Shouldn't use intuition for conditional.
You will win a goat.
Huh?
You will win a goat if you
Or lose the goat. But what you should do is use this definition. And this definition is very useful to understand things about conditional expectation. This definition told us that there exists a unique such object, or if two such objects have these two properties, they're G measurable and they have this property, then they're equal up to measure 0, right? Okay, so we can use this to determine many, many, many things about random variable. So let me give just a few properties. Okay, First, we give some exercises, which are very easy. Some I will solve. Okay, so exercise 1 is if X is G measurable. If X is already G measurable, then it doesn't have to be, right? Because G is smaller, but it could be G measurable. And then the exercise is to show that what is the conditional expectation? Just X. And I have to write here almost shortly, right? Because it's only up to measure 0. Okay?
חבר הכנסת טל הולך עם החבר'ה האחרים. אני לא יודע לאן, אבל תקשר.
Okay, so if you think about it, if I know all the information of G, what is the average value of X? Well, it's the value of X because I know X as well. For me, X is a constant now. It's not a random anymore. I know everything in G, and X is G measurable. Okay, but again, that's intuition, which is not necessarily good. And you can just prove this using the fact that X is G measurable and satisfies. Plug in an X here, right? And of course, these two things are equal. Okay, so since the theorem, which I didn't prove, guarantees uniqueness of this object, well, uniqueness you can prove, you can easily prove. You can prove if you have two objects that satisfy that they're both G measurable and they satisfy this property, then they're the same up to measure 0. The problem is, does there always exist one? That you use a Radon-Nikodym derivative, but I'll skip the proof of that. Okay. And I could show it to you if you really want. But another thing is that maybe this is 1, 2, if X is independent of G, this just means that if you take any event in G and you take X, then the indicator of that event and X are independent random variables. Okay. So X is independent of G, then the expectation of X with respect to G, well, now this does not give you any information about X. And so actually this thing becomes a constant. And the constant is just the expectation of X. The new balancing point, if you're in, and I tell you, you have to rebalance according to the information you have. Well, your information isn't really telling you anything about X because they're independent. Okay. And specifically, if X is a constant, right, then it's independent of anything. A constant random variable will just, the expectation of constants is constant and the conditional expectation of constants is constant. Okay. Another exercise is to show, well, I have a random variable and I didn't prove it, but it is an L1 random variable. So I can ask, what is its expectation, right? I have this random variable. I can ask, what is its expectation? Many times I will just forget these two brackets here, okay? Well, then it's just the expectation of X. Okay, so the new conditioned random variable, if you average, what are you averaging? You're averaging the information, and you get the original average of the measurement. Okay. Because averages of averages are the average. Well, okay, this is it may be more tricky. You have to think about how to prove this, but I'll leave it as an exercise. Conditional expectation is linear. Conditional expectation is linear. These are L1 random variables, okay? So linear. So some properties. I'm not proving these things because they're not very difficult and you can find the solution in the books. But so we have Jansen's inequality, and specifically we can do so we can pull the absolute values inside. So you see, if I take expectation of this, then it's expectation of that, but that expectation of that is just the expectation of the absolute value of x, which we started with. Remember, the definition was only for integrable random variables. So this shows you that if you start, since you started with an integrable random variable, you get integrable. Okay. Now I should give a remark here. The way I defined it was for L1 random variables, which is the most general. Remember, in probability, L1 is the biggest restriction, is the smallest restriction, right? If you're in L2, you're in L1. But if we were content with talking about L2 random variables, L2 is a Hilbert space. Okay, L2 is a Hilbert space, at least modulo the constant functions or something like that. Right? L2 of random variables. So, or yeah, modulo measure zero. Right? So L2 is a Hilbert space, and what you can talk about is the orthogonal projection to the G measurable, to the subspace of G measurable L2 random variables. It will exactly be the conditional expectation. So if you restrict yourselves a bit more and talk only about L2 random variables, then conditional expectation is just orthogonal projection to a subspace. Okay, but the L1 definition is more general. This shows you that it's an L1. I wanted to say it's linear, right? So conditional expectation of AX plus Y, condition on G, is the conditional expectation and there's monotonicity also. So where is it? Yeah, so monotone convergence, right? So if X is less than or equal to Y almost surely, then the conditional expectation of X is less than or equal to the conditional expectation of Y almost surely. Okay? I always have to write almost surely. These are random variables. These are not numbers. And 4, if I have monotone Yn converge monotonely to Y and they are non-negative. Probability 1, did I write Y? Then the conditional expectation of these guys also converges monotonely. Well, it's monotone because of the previous thing, but it converges. So this is monotone convergence for. And you basically prove everything just the same way as you would. I don't know why I did Y. Okay. Let's prove a nice, very, very important thing, and this captures some intuition. So let's do this next exercise. I mean, for all of these, you basically just show that the correct objects have the right property, right? That they're everything is G measurable when you condition, because you know that it's G measurable, and you have to show that, you know, if you put the indicator of an event there, you get the same expectation. Okay, so let's understand. So size, I guess. So assume that we have X times Y is L1. So for example, if they're in L2 or something like that. Y is G measurable. Okay, so conditioning on G, Y looks like a constant. We know Y, we know the actual value of Y because there's no randomness if we condition on all the information in G. Part of that information is 1. Okay, how do we capture that? Well, then the conditional expectation of x, y conditioned on g is exactly equal to the y. You can pull the y out. It's like a constant inside the expectation. Okay, and you're left with the conditional expectation of x condition. And this is almost surely, of course.
You have to have X in L1, right?
Yeah. Well, I mean, this was the assumption for everything. Okay, so maybe we right, so let's do this solution to this one. Just to see how these things work. So first of all, what do I need to show? This is a random variable, right? I need to show that this guy, if I want to show that it's equal to this guy, I just need to show that this guy has the right properties. So first of all, it's G measurable. Why is it G measurable? Well, that's very easy. This is G measurable under assumption, and this is G measurable by definition. So their product is also G measurable, right? So all I need to show is that indicators do the right thing, right? So I take some A in G, right? And then I compute the expectation of this times the indicator of A, and then the expectation of all of this times the indicator of A, and check what happens. Right? So, so now we have 4 cases. Case 1, Y is indicator of some event. Now this event, Y is G measurable, so this event is also from G, right? Of course, this is not the general case. Just saying, start with this. This is another thing I say to my students in probability. I always tell them, well, if you can't on the exam, if you can't prove the general case, try starting with simpler cases. Show me you know something. Okay, so let's start with a simple case. Y is an indicator. Okay, Y is an indicator. Then when we look at X, Y times the indicator of A, this is right. This is what we want to show is equal to the expectation of this times the indicator, this whole thing times the indicator of A, right? That's what we want to show. So this time, this is the same thing as the expectation of X times the indicator of A intersection B, because product of indicators is indicator of the intersection, right? Just one if and only if both A and B happen, right? So this is just equality, but A intersection B is in G. So by conditional expectation, this is definition of conditional expectation, right? But now I can turn this into the product of indicator A, indicator B. Indicator B is Y. Okay. Saying here, oh yeah, and then this is equal to, yeah. What am I trying to prove? I'm trying to prove Y times something. So I take indicator B, which is Y, I put it here, it's just products are commutative. And I have indicator A here, and this is what I was trying to do. This, if the A's are always the same thing, and this is G measurable, so this is a version of the conditional expectation of X, Y with respect to G. The uniqueness property to say that this is a version of that. Okay. Whatever happens to be here, if it satisfies this equality for every A, then it's a version of the conditional expectation. So this shows you how, well, at least for indicators, how you put something G measurable here for if it's an indicator, it pops out as a constant because you know what it is. You know what's going on. The constant in Newton. Okay, so this is case 1. What about if Y is a linear combination of indicators? What do I do then?
Linearity of conditional expectation.
Right?
Linearity of conditional.
Right, exactly. And use linearity of condition, right? So for finite sums of finite linear combinations of indicators, I can So case 2 is finite linear combinations of indicators. Right? Why? Okay, that's easy, just linearity of expectation, was what the previous exercise. And case 3, as usual, you take almost surely non-negative random variables, and there's the classical trick of writing y as well, this is my favorite, but you can do whatever you want, and minimum, right? And you can check that this sequence of random variables is almost surely non-negative, almost surely converges to y, and in a monotone fashion. So now you use monotone convergence, which was also the previous exercise. So yeah, so
How do you know those yn are finite linear combination of indicators?
well, they only take finitely many values. So they're simple random variables. Have to be careful here because we're doing xy. So
And it's only for y.
yeah. So we have to be careful. So this is good when y is almost surely non-negative and x is almost surely non-negative as well. Okay, because then when you do this approximation, then you get x, y, n. Here the y-n's pop out from case 2, and this converges to xy, right? And when the yn, okay, so this is equal to yn, conditional expectation, right? And this converges y timesyn's converged y. Okay, so this is monotone convergence. This is regular just pointwise convergence, and so you get that these two have to be the same up to measure 0. Okay, and now case, what is it, 4? Is if we have general x y, right? And what do we do? Well, we write xy is x plus minus x minus, and y plus minus y minus. These are non-negative, these are non-negative. They're all integrable because it's equivalent to being, 1. They all have finite expectations, and then you have a linear combination of 4 terms, each one which has a x plus or minus and a y plus or minus. And each, when you take the conditional expectation, right? So this will have 4 terms in it, 4 conditional expectations by linearity, which will have a plus or minus, and an x or a y in each of them. And each one of those, the y's come out because of the previous. Okay, leave you with the details. Straightforward. And this is basically what you do in every single proof in measure theory almost, right? You do 4 steps, maybe 5. Okay. Yeah.
About this monotone convergence. Monotone convergence, as I know it, is the one with the expectations, right? So here you get pointwise convergence, that's the property you wrote.
Monotone convergence for conditional expectation, which was the previous exercise. And the previous exercise told me that if I have a monotonely converging sequence of non-negative random variables, which is in this case x times yn, because x is non-negative, this is a monotonely converging sequence, to this. then the conditional expectations also converge almost surely. Pointwise here means almost surely, I mean, because you're only defining things up to measure zero. Okay, that was what the theorem, it was an exercise here. We can prove it, but you basically just, it's the same, it's the same proof that you would know. All these things are the same proof, and they're all in the book. If you look at the chapter 2, or the chapter about martingales, then I think it's chapter 2. I have an older version, and the chapters are different. I have to download the newer version. Okay. What else did I want to do? So an important case, so a special case, so position or theorem, special case. So the special case is where G is generated by a sequence of events. Okay, have some sequence of events. These events are pairwise where A, N are pairwise disjoint, and the sum of their probabilities is 1. So what does this mean? This is basically a partition of the space, is what I call an almost partition, right? There could be some leftovers of measure 0, but basically it partitions the space into countably many parts. So, right? So what should the expectation, you condition on this information, what should it be? Well, what you should do is what this tells you is that you don't know everything. You don't know how to differentiate between things in the same event, right? But you do know what is conditioning on G. It's saying you do know which of these events happened. Only one can happen, right? Partition, the pairwise disjoint. But you do know which one happened. And if A1 happened, you have some expectation for your X. If A2 happened, you have a different expectation for your X. What is the expectation? Well, the expectation should be the corresponding restriction to X onto the event AN that happened, right? Normalized to be a probability distribution, right? It should be just basically the conditional expectation of X conditioning on an event, which is, you can think of why, how you can try to define such a thing, okay? So it's a new probability measure on the space, and you get a different probability measure depending on which event happened. So you have this situation, then again, for any Lx in L1, where everything is defined, I'm being very informal. But if you want to do the expectation of X conditioned on this thing, then what you need to do is you have to go over all the events. You have to check which one happened, right? This is a random variable. This is a random variable. So I'm plugging in a little omega here. It says, okay, look at which one of these happened. Okay, right? Because all of these will be 0 except for 1, or maybe all of them will be 0, but that's measure 0. And then in the case that this one lit up, this one was 1, right? This A5, say, right? What do? You take the expectation of X indicator AN and renormalize this to be a distribution, probability distribution. Okay? This is the if I know that AN happened, this quotient is kind of the average of X knowing that AN happened. Right? That's what it is. How you would define.
So you want them, all of them also to be on the measure, on positive measure, right? Positive measure.
Yeah. I should write it like that. Well, I could leave some that are measure 0, but just sum over all of these. If they're measure 0, I don't need them in the sum.
Yeah.
Okay. I should actually correct that, yeah. I hope I corrected it in the... Okay, so how do we we need to prove an equality between two random variables, right? We want to show that this is a version of conditional expectation. So first we need to show that this is G measurable. Well, all of these are in G, so this is a G measurable, just an infinite sum of G measurable random variables, right? And so we need to show that it satisfies the property of this, if I multiply it by an indicator of an event from G, right? So, let's define two probability measures. The trick here that we define two probability measures. Fine. Yeah, let's call this Y. Just I don't need to write it all the time. I want to prove that Y is the conditional expectation of X, and I'm going to define a probability measure. So P is going to be an event from G, going to be just okay, and this sorry. No. P of B, you want it to be a function of B. Okay, if the expectation of X is 0, okay, so I want to assume that the yeah, case 1, X is non-negative, and the expectation is bigger than, I mean, if the expectation of X is 0 when it's non-negative, then it's 0 almost surely. Okay, so we started first with this case. Okay, and then the general case will just follow by writing X is X plus minus X minus. So this will be the difference between two conditional expectations. And this will also factor into two different sums, each one of them with a corresponding conditional expectation. So we get they're equal. Well, we really only need to do this case. And now this defines a nice probability measure. You can check that this defines a probability measure on, so this is probability measure on omega G subsegment. Now define another probability measure, Q. This will be the expectation of Y, indicator B, divided by the expectation of, I want to write Y, but I'll just write X. How do I know? Because if I take expectation on this side, right, then all of these cancel, and I just get the sum of the indicator is 1 almost surely, so I get the expectation of X. So Y and X have the same expectation. Okay. This defines also, this is also a probability measure. And now, for any P of AN, well, what is it? It's plugging in an AN here, right? And for Y, when I plug in a Y and I multiply Y by an indicator of AN, then the indicators are the intersections, they're pairwise disjoint, so only one survives, that AN. You just get the corresponding thing here, right? So P of AN is equal to Q of AN for every N. Just do the computation and you see that it's the same. Okay? And of course, they both give 0 measure to the empty set. So you have that G is, let's write it this way, G is generated by the pi system which generates G. Right? Pi system is just a system which is closed under intersections. any two intersect here. Reveal the empty set. Okay? Now there's a theorem which I mean, sometimes it's called the pi lambda theorem, sometimes it's called Dinkin's lemma, which tells you that if you have two probability measures which identify on a pi system, then they also identify on the sigma algebra generated by that pi system. In this case, in fact, it's much more intuitive than that, because you can see that all the events in G, you can kind of get from, you know, disjoint unions and stuff of the A's, right? And unions, intersections, things like that, right? And so you can kind of maybe prove something by induction here or something like that, or at least get a feel for it. As soon as you're kind of on the elementary building blocks, building G, which are all disjoint, you have the same probability measure. There's no other way to extend it to a probability measure on all of G. You know the values of a probability measure on all the A's, then there's only one way to extend it to probability, you know, for example, to finite unions of those things, there's only one way to do it, right? Because they're all disjoint. You have to add them. Okay? It's the same phenomenon that happens when you have a probability measure on a countable space, and you tell me what the probability measure of all the singletons is. You know the weight of every singleton, right? Then you know every subset, because it's just the sum of its elements. Okay? So, but in general, theorems I can write by Dinkin's lemma. Or the pi lambda theorem, or whatever it is. Because this is a pi system, and they say the same thing for the pi system, they say the same thing for the sigma algebra generated by the pi system. So P of B is going to be equal to Q of B for every B in G. What does this mean? This means that for every event in G, if I look at the expectation of Y indicator of the event B, well, what is this? By definition, this is the expectation of X times Q of B. This I know is the same as the expectation of X times P of B. And this is the same as the expectation of X indicator B. And since this is true for any event in G, this means that Y is a version of the conditional expectation of X. That shows, and this formula that is fortunately erased is a nice way to understand. If you kind of have, and I think some people like to think about it like this. I want to say names because maybe they don't like to think about it like this, but I have in mind. So you have omega, and you have this like partition of omega. Right? Maybe there's some measure zero left over, but I don't care about that, right? And so these are my ANs, and I condition on the sigma algebra generated by these things. What does it mean? It means I tell you the information at the resolution of these pieces, you know where your random omega came from. You know in which piece it lies. You don't know how to differentiate the resolution with higher than that. Right? So inside the piece, you don't know exactly where it is. And you have some measurement, or think you have some event. Think of X as being an indicator of some event. So you have some event which is not G measurable, right? So it doesn't respect this partition. It's not necessarily G measurable, so maybe it looks like this. Right? You can think of that as being your X. What is X? X is, instead of being an event, it's just like a different weighting of, right, different numbers spread across these different values of omega. And you want to kind of average these numbers, or you want to say, what is the weight of this purple event here? And the way you do it is I know the information, which piece. So tell me which piece. Oh, it's this piece? Okay, good. So in this piece, I need to measure this side. I know that this piece happened, right? So I need the relative weight of the purple event inside the piece that I know which happened, right? Which is exactly just taking your random variable, multiplying it by 1 if it's in the correct place and 0 otherwise, and then renormalizing so that this whole piece has weight 1, probability measure, right? So that's what conditional expectation is doing. It's kind of telling you which piece are you looking at. All it's doing. Okay?
Can you explain again the first equality, the expectation of y times
This,
yeah.
well, this is the definition of Q. Q was defined to be this quotient, so this is just equal to that. Oh, I built it. I really used the fact. The expectation of y in this case, remember y was the sum with indicators, is the expectation of x. So I used this fact. Okay, so this is conditional expectation. Very, very useful thing. Let me give another definition and example. So if x is one random variable, and y is another random variable, right, then I can condition x on y. What does it mean to condition and define? Conditional expectation of x with respect to y. Okay? This is equal to, find to be, the conditional expectation of x with respect to the sigma algebra generated by y. Sigma algebra generated by y is just all the pullbacks of Borel sets by y. Okay, I should remind you that when I talk about L1, these are well, we could say complex valued, but real valued random functions, right? We cannot take expectations. We don't define expectations for like general valued random variables, or some people could do it for, you could do it for Hilbert spaces or for Banach spaces or for finite dimensional vector spaces. It's possible, but we're not going to ever talk about expectations. If I really want to talk about kind of the average of a random vector, I will explicitly write it out. Okay, so whenever I take L1, these guys live these are functions from omega to R, say, okay? But y here, I never take averages of y, so y I could let be kind of a function into a different space, okay? So in fact, what I'm going to do is y, I could let y from omega to some g, yg, who knows, but I could let y be just a measurable function. Okay, and now what does this mean? This means that hidden here, there is some sigma algebra on G. In the future, G is going to be a group, and the sigma algebra is just going to be all subsets, right? Because it's going to be a countable group. Okay, that's why I wrote G. You can take a general valued random object, which is what you can think of this, right? A general valued random object, and you can condition on it this way. And what would sigma of y be? Sigma of y is you pull back all of the events in the sigma algebra that you're talking about here, pull them back to events in F, which is what measurable means, right? And you get a new sigma algebra, sub-sigma algebra on G. Okay, that's what sigma of y. Basically, conditioning on a random object is just conditioning on all the information that object contains. Generate the smallest sigma algebra you must have if you know that object.
It's just
Now G is a general set. There is a, when I write measurable function, it means there is this measurable structure on G. It means there's a sigma algebra on G that we're talking about. There's something in the background. What's going to happen is G is going to be a countable set, and the sigma algebra is just going to be all subsets. So this is just generated by pulling back all singletons. Just generate. Okay, or just pull back all the subsets of G by the function y. You get some sub-sigma algebra of F, and okay.
I think also when you have like a density function, you can look at the two-dimensional on the variable x comma y, and look at the expectation of the random variable x with conditioned on y.
Yeah. So that's what I'm going to say. That's what I'm going to say next. That's
And
what
this is a function of y, of small y, and then you can apply it to y.
so
The same thing.
I don't remember who here took my probability course, but in my course, I teach conditional expectation in some cases and not in others. And there, what we do, for example, if we have y, so example, y from omega to r is discrete, which basically just means that there is a countable set which y falls into with probability 1. Okay, so if y is discrete, then what you do is the sigma algebra of y is generated by pulling back all the Borel sets, but it's enough to pull back the singletons because y only lands in countably many things. So this sigma algebra is the same sigma algebra as the one generated by y equals little y for all y in R. And in fact, there could be, you only need countably many such guys because most of these are empty, or at least up to measure 0, right? So this sigma algebra up to measure 0, or you can change y to be, okay, so let's actually assume that y of omega is countable. Okay, just to get away, we could change y by measure 0 and have this, right? And so instead of looking at this, we could, these guys could come from some set which we call ry, and ry is just all those which are not empty, right? ry, so ry is countable, okay? And the range of 1, okay? So this is what's going to happen, okay? And if we go to the more general case where it's discrete, where this is only up to measure 0, then these are not the same sigma algebra, but the conditional expectations will be the same. So maybe I should have given that as an exercise. You have two conditional G and G prime, and they're the same up to measure 0, meaning that for every event in G, there's a corresponding event in G prime such that the symmetric difference between the events has measure 0. Then and the conditional expectation of x with respect to G is going to be the same as the conditional expectation of x with respect to G prime. Why? Because remember, when you multiply by little indicators of events, you can always move from an event A to an event A prime, and they have the same, the indicators are equal up to measure 0, so you get the same result in the expectations. Okay? So basically what you have here is this, and then the conditional expectation by the previous formula that we have, any random variable. In my course, I usually do it for 2 discrete random variables, right? Right? So if you condition on y, now what do you want to say here? You want to say, well, what is this conditioned random, what is this new random variable, this conditioned random variable, x conditional on y? You tell me what happened to y, and I tell you that the new measure is the probability that x is equal to something is the same probability conditioned on the event y is equal to what you told me. Okay? So what is this thing? This is, you sum over all possible y's. Well, which y's are possible? Only those guys, right? And if that's what happened, so only looking at this event, right? Zero otherwise, if that's what happened, then the new distribution of x is just x conditioned on y, big Y equal to little y, which is the same thing as saying, you know, putting an indicator here and dividing by that probability. And you need these to be positive, of course, which is, so maybe we need to change here. Move that zeros, okay? So, but this is exactly the formula that I had before. So this extends the notions I teach in my course, not to say that this is a good definition, but rather that what I teach is a simple case of this, so that I don't have to go into all the really details. But since everybody here is more mature, I think you can handle these things. And this is the way I like to think about these things. You have some discrete object, right? For a discrete object, it's very easy. The resolution is just look at, you know, where did it land? And for each point that it landed, I can like re-average my guy. So it's a random thing, because in order to know what this average comes out to be, I need to know what happened to y, right? So I sample y, and then when I know what y did, I can average x knowing that information. Okay? That's how I like to think about these things. And you can extend it to continuous objects as well. And now you're not restricted by having a, continuous density or having anything. You just can always define conditional. And in fact, you can do it in a very, very big general. We will want to do this. And for us, the discrete case will be enough. Countable case will be enough. So we'll just have countable sigma algebra generated by countably many events. And so we'll have some kind of formula like that, but we will want to understand, what happens. And we also want to take limits, and then we countable things won't be. So we do need the sigma algebras at some point. Okay. So tomorrow we meet at 10.
Thank you.
And here, we meet here.